तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So we have been looking at Hamiltonian systems, and just to put things in reference, we have h of qp. Sometimes if it is non-autonomous you also have a t, so this will imply non-autonomous case, but most of the time we are going to look at autonomous situations. And we saw that Hamilton's equations of motion where qi dot is delta h over delta pi and pi dot equal to minus delta h over delta qi for 1 less than equal to I less than equal to n. We also saw, just to recapitulate, that in the case when h was a function of q and p alone, the autonomous case, this implied that dh over dt is equal to 0. In other words, the Hamiltonian was a constant of the motion on the solution set of Hamilton's equations. We further saw that the general equation of motion for any function of the dynamical variables and possibly time, the rate of change of this quantity was equal to the Poisson bracket on this side of f with h plus delta f over delta t. Okay. And of course if this is a constant of the motion, if it is a constant of the motion, then this quantity on the right hand side should vanish. In particular, if f is a function of just the q's and p's and not t, then it is a constant of the motion if and only if its Poisson bracket with the Hamiltonian vanishes identically. So this was our the point to which we had got. I would like to mention right here that if you look at it in general, there are constants of the motion which are time dependent, explicitly time dependent, and you have to appreciate the fact that if you have motion, for instance, in the qp space, there is some kind of phase trajectory, but you could also look at it in an extended phase space with all the q's, all the p's and time itself as one of the coordinates. Then in that space, if you have a t here as well and a q and a p here, in this space too the phase trajectory is a one dimensional curve. And now you could ask, how is this one dimensional curve formed? It is obviously formed by taking a set of constants of the motion, and the mutual intersection of all these constants of the motion, the surfaces, would give you the trajectory. Okay. Now this phase space is 2n dimensional, n of these and n of that, and the phase trajectory is a one dimensional object being a curve, and therefore you know that you must have 2n minus 1 constants of the motion whose mutual intersection would give you the phase trajectory in principle. In this case the phase space is extended phase space, and this is 2n plus 1 dimensional extended phase space. And how many constants of the motion do you need here in order to specify the trajectory? 2n of them, and at least one of them must be time dependent, because if all of them are explicitly time independent, they would be so here too. And if you have 2n time independent quantities here, their mutual intersection would generically be points, they would not be curves. You have too much data and then there is no motion at all. So it is clear for any physical system you must have at least one constant of the motion that is time dependent explicitly time dependent. You could have more, but you certainly must have at least one. And let us look at a very simple example. You already know this, but let us look at an extremely simple example of a particle moving on a line, a free particle moving on a line. So I have a single q and a p, and the Hamiltonian in this case h of qp is just p squared over 2m. Its motion on a line and its free motion on a line. A simple example, there is no potential, so it is a particle which is no force at all, moves on the x axis, I will call it the q axis just to keep in touch with this notation. And then what do the phase trajectories look like? Here is q, here is p. What do they look like? Just straight lines. And what is the constant of the motion? P itself. P is a constant of the motion. In fact, p squared over 2m is a constant of the motion, but better still, p itself is a constant of the motion. And the reason of course is in Hamilton's equations. You have q dot equal to delta h over delta p equal to p over m, and p dot is minus delta h over delta q, and q is now a cyclic coordinate because there is no q dependence in the Hamiltonian, and therefore this is 0 by definition. This would imply p equal to a constant. What determines the initial value of p? What determines the value of p? The initial condition, whatever be the initial condition. And what do the trajectories look like? Just straight lines parallel to the q axis, either this way or that way, depending on whether the initial p 0 is positive or negative. So the whole plane is striated by these lines. These are the phase trajectories. However, if I look at it in extended phase space, so here is q, here is p, and here is t in this direction coming out, then the phase trajectory is still a line in this extended phase space, but now you need two constants of the motion. One of them is a Hamiltonian, or p, it does not matter, p is a constant. Now what sort of object is p equal to constant in this 3-dimensional space? They are actually planes. So whatever was this line becomes a plane, p equal to constant passing through that point. That is not enough to specify the trajectory. You need one more constant of the motion, and it is clear in order for it to come out of the t of the board, it must be t dependent. It must be some other plane which cuts this plane and produces the trajectory for you. It must be some other surface. What quantity is that? What is that quantity? What is the other constant of the motion? Well, you can do that by solving this equation. So let us put this p equal to constant equal to p naught, the initial value, back in this equation, and then together these two things would imply that q of t equal to q naught plus pt over m, because p is constant. You could have written p naught there, it does not matter, pt over m. So now tell me what is the other constant of the motion? Well, it is actually sitting there. So what is the constant of the motion? Q naught is a constant of the motion, but it is not nice to say the initial condition is a constant of the motion. A constant of the motion is a function of the dynamical variables and maybe time. So q minus pt over m. This implies that q minus pt over m equal to constant of the motion, and it is directly determined by q naught. So this example illustrates to you what I mean by a constant of the motion, not the initial condition. The initial condition determines the numerical values of constants of the motion, but constants of the motion are functions of the dynamical variables and of course time possibly. But you see here q, p and t are respectively dynamical variables and the time, and it is explicitly time dependent. This object is explicitly time dependent. So the intersection of this surface in the QPT space with this surface p equal to constant in the QPT space gives you the phase trajectory. So is this clear? You see why there must be at least one constant of the motion that depends on time explicitly. So do not be surprised if constants of the motion depend on time explicitly. Incidentally, we could apply this to check if that guy is really a constant of the motion. We could apply this formula. So what would this give you? In this case I claim that this is f, and therefore what is f with h? This is equal to q minus pt over m, Poisson bracket with p squared over 2m. And what is that equal to? Well, remember our basic rules, the canonical, the standard commutation relations, the Poisson bracket relations. We had qi with qj was 0, pi with pj was 0, and qi with pj was equal to the Kronecker delta ij. In our problem there is only one q and only one p, so there is no need for I and j. It says q with q is 0, that is obvious. So with p, q with p is 1 on the right hand side. So what does that get us? This thing here, clearly t does not play a role, it is not a dynamical variable. P with p squared is 0 because p commutes with its Poisson commutes with itself, and therefore this reduces to q with p squared over 2m. But 1 over 2m is a constant, that does not do anything, it just comes out of the bracket. Therefore you have q with p squared and a 1 over 2m. How do I simplify that? Q with p I know, but what about q with p squared? I use this chain rule that I wrote down the last time. So this becomes equal to 1 over 2m q with p, a p outside, plus a p times a q with a p. I write that p squared as p times p, and you have to do this with each of them, and q with p is 1. So this guy is 1 and this is 1, there is a bracket around the whole thing, okay. And therefore I get a 2p inside and a 2m outside, so that is equal to p over m. That is not 0, that is not 0, and that is because this f has explicit t dependence. So we discovered that this quantity here is equal to p over m. But what is delta f over delta t? Minus p over m, your partial derivative with respect to t, minus p over m, they cancel and then you get a constant of the motion. So you see how this works, you need this extra term, and then the total derivative of this is 0. So what has happened in this problem is utterly trivial. The explicit t dependence gave you a minus p over m, and this guy here gave you a plus p over m, and they cancelled. Another way of saying it is, in this combination q minus pt over m, the t dependence of q cancels the explicit t dependence of the term minus pt over m, and therefore you have a constant. So this is going to be like a general rule. In n dimensions, when you have a phase space of n dimensions and an extended phase space of 2n plus 1 dimensions, there must be at least one constant of the motion that is time dependent, and that is how motion occurs, and the mutual intersection of all these surfaces will give you the trajectory, okay. Now of course immediately you realize that this can lead to incredibly complicated behavior. The reason is, as you can visualize, even if they are simple surfaces, when they start intersecting with each other there will be all sorts of little complications in the intersection, and that is how in generality it turns out that in a higher dimensional phase space, phase trajectories have exceedingly complicated behavior. Even if the constants of the motion look relatively simple, the intersection can be very, very complex, and then very often it will turn out that the constants of the motion themselves are not isolating integrals. I will explain what I mean by isolating integrals, that is our next task, okay. Okay, now given this, I have to say a few things about how we could go about solving Hamilton's equations of motion, and then we go to some examples. But first a little more formalism. How would you solve a set of equations of this kind? It is quite intricate, and the reason is, except in the simplest instances, this is some horrible function of all the q's and p's, and it is a very nonlinear function, and so is this. and therefore you discover that the problem is quite intricate. Solving this set of equations is not possible except numerically in most cases, but here is what happens in some instances, and it turns out that is the only way in which this set of equations is explicitly integrable, and this is what can happen. Like in all these problems with many variables, it may be possible to change variables and write the answer down write the problem down in terms of a simpler set of equations. So you might want to, for instance, use this fact that if there is a cyclic coordinate, if there is any coordinate q on which the Hamiltonian does not depend, the corresponding p, the conjugate p, is a constant of the motion. So it would be very nice if you could change coordinates, if you could change variables to a new set of variables such that the Hamiltonian does not depend on some of them. In other words, the idea is to try to produce cyclic coordinates, but you can't in general do this for an arbitrary Hamiltonian. You might want to do this by changing variables, but you do not want to change variables in an arbitrary fashion. You would like to preserve some of the properties of this set of equations. What is the primary property of this set of equations? Well, if it is first order, you would like to preserve that. I would like to preserve the structure of these equations, because I know that for autonomous systems h is a constant of the motion. I do not want to lose that, I would like to preserve that. So let me for a while talk about what happens when you have autonomous Hamiltonians, and then we come back to non-autonomous situations like this. I would like to use this fact, I would like to use this thing here. Even independent of this fact, the flow in this phase space, is it conservative or dissipative? We can easily check this out, because remember we had a general criterion for checking out whether flows were conservative or dissipative. What do you think is going to happen? Well, here is what is going to happen. I took a flow like this, of this kind, if it was an autonomous flow, and then I said, okay, this flow is conservative in the sense that any volume element delta V, which was defined as delta x1 product up to delta xn, this volume element remained unchanged as time went on, provided the divergence of f was 0. If del dot f was 0 in phase space in the capital N variables. Let us ask if that is true. Let us ask if that is really true here. Well, let us look at conservative, let us look at autonomous Hamiltonians first and ask, is this true? What should you do? So I have del dot f in the present case, in this case, is equal to, remember that the coordinates in my problem, the coordinates are x equal to q1 up to qn, p1 up to pn. And what is the del operator? The derivatives with respect to these guys. So delta over delta q1, delta over delta p1 up to delta over delta pn. Okay. Now what happens if I did del dot f? I must do delta f1 over delta x1. So the first term is delta f1 over delta x1, but x1 is q1 and f1 is delta h over delta p1. So this gives me d2h over delta, I have to do q1 delta p1 plus all the way up to d2h over delta qn delta pn, and then I go on to the next one, which is delta fn little n, n plus 1 over delta x little n plus 1. But what is that equal to? That is equal to a minus delta h over delta q1 differentiated with respect to p1. So the next term is minus d2h over delta P1 delta Q1 up to d with a minus sign d to h over delta Pn delta Qn. And what is the answer? Zero. This guy cancels that because you can take partial derivatives in either order. So this is identically 0. Hamiltonian flow therefore is volume preserving in phase space. Very crucial observation. And now you see begin to see the importance of these minus signs, which followed by the way from the Euler-Lagrange equations. These things cancel out in pairs automatically. So it gives us this very crucial piece of information that a Hamiltonian flow preserves volume in phase space, and I already mentioned that a volume preserving flow in phase space is the analog of in fluid dynamics an incompressible fluid. It is as if in phase space the volume elements are like the flow of an incompressible fluid. They could change in shape, you know, a fluid element can change in shape as it goes along, but its total volume must remain the same. Any initial volume you take must flow along such that the volume does not change. Could change very badly in shape as we will see, but it must remain constant. So that is our first important lesson. A Hamiltonian flow is volume preserving in phase space, of course. Of course you could say, look, you proved this for an autonomous Hamiltonian system. I used the fact that the Hamiltonian system was autonomous somewhere along the line. I used this here. This theorem was true for autonomous systems. What if the system is non-autonomous? What would you then say? Well, the magic is a Hamiltonian flow continues to be volume preserving even if the flow is non-autonomous. And that is not hard to see, because suppose you took some point here, this is your initial point Q0 P0, and you went to some point Q1 P1. I shouldn't use this symbol, let us call it Q at time 0, P at time 0, and it went to a point which is Q at time 1, say P at time 1. A little time delta t later, so this was at t0, this is at time t0, and that was at time t1. And let us say t1 is separated from t0 by a delta t, an infinitesimal interval of time. So this is an infinitesimal line element in phase space, part of a trajectory. Then this point is determined by this point by Hamilton's equations, and let me write it down without the ij for a moment so you see exactly what is happening. So what is q at 1? This is equal to q at time 0 plus delta q over q dot multiplied by delta t, right? But what is q dot? Delta h over delta p, and this is at 0. By 0 I mean at time 0, time t0, and the point is p0 and q0 times delta t plus order delta t whole squared. And similarly p at time 1 is p at time 0 plus delta h over delta p. Am I making sense here? Delta dp over p dot, which is minus, and this is delta h over delta q at t0 delta t plus order delta t whole squared. Okay. Now I can regard the point P1 Q1 P1 as having been obtained from Q0 P0 by a certain change of variables induced by the Hamiltonian, I can imagine that this is a new set of variables which has come out from the old set of variables by a certain transformation, and therefore I can find the Jacobian matrix of this transformation. So I can actually find delta q1 p1 over delta q0 p0. I can find this transformation. This is the transformation matrix. It is going to be a 2n by 2n matrix. I find all these partial derivatives, and that is what the Jacobian matrix is. Now the initial volume element is related to the final volume element by a simple relation which says the final volume element is equal to the initial volume element multiplied by the determinant of this Jacobian matrix. That is how volumes change. And now I leave it to you as a very simple exercise to show that the Jacobian of this matrix is 1 plus order delta t whole squared. Because of this minus sign, the cross term cancels out, the order delta t term cancels out, and it says the volume is preserved. And if it is preserved in every delta t, then you can see it is preserved along the entire trajectory, because you can do this delta t at a time.
When is this reasonable?
Pardon me?
When is it reasonable to assume that delta t squared and higher order terms don't?
It is called calculus.
No, but
Delta t is a first order infinitesimal, and if I choose delta t sufficiently small in the limit going to 0, then the Jacobian matrix is 1 plus higher order infinitesimals, which will go to 0 if I divide by delta t.
what if d square h by dp square blew up?
Very good point. He says, what if that second derivative blew up? Now our assumption throughout is that the Hamiltonian is a nice differentiable function, all the second derivatives exist. We have assumed that. Right from the beginning we have assumed it. There could be isolated points where the matter becomes singular, then it is no longer true. Just as even to go from the Lagrangian to the Hamiltonian, I needed to assume that the Hessian matrix was not singular. So there is an assumption, namely that all these h's and so on are smooth functions, they are differentiable, at least twice differentiable. Later we will see I am going to require something like analytic behavior, but for the moment twice differentiable. So modulo mathematical problems of this kind, in general, generically this is going to happen. So the lesson I want to mention here at the end of it is this statement is true whether or not the Hamiltonian is autonomous. Even if it is time dependent explicitly, that statement is still true. It is a very powerful statement, and you will see where it is going to lead us. Okay. So in that sense, this structure here was extremely helpful, and now if I make a change of variables, I would like to preserve this. I would like to preserve this property that this is like an incompressible fluid. Therefore I am now going to define a set of properties I would like to deduce, I would like to impose on any transformation, which is going to keep my system manageable, and this defines what is called a canonical transformation. So let me define these. One, we would like to change variables from the set QP, all 2n of them, to a new set QP such that the first thing we would like to have is that the Jacobian matrix delta QP over delta QP, this matrix has determinant equal to +1. This ensures that it is volume preserving. Incidentally, it could be -1 and it would still preserve the volume in magnitude. When you took this magnitude, this determinant could have value -1 and it would still preserve the volume, but what would it change? What would it change if it became -1? What would it mean? It would change what is called orientation. It is like going from a right-handed coordinate system to a left-handed coordinate system. It is like doing a parity transformation. Suppose in 3 dimensions you start with a set of coordinates x, y, z, and I choose a new set x prime is minus x, y prime is minus y, and z prime is minus z, then a volume element does not change, but the product dx dy dz is minus the product dx prime dy prime dz prime. It changes orientation. I would like to make it +1 for reasons which we are not clear right now, but we will impose this. Orientation should also be preserved. That is the first thing I would like to have. I would like to have a little more. I would like to ensure that the structure of Hamilton's equations is not changed. I would like to ensure that. What would the new Hamiltonian be? So what is really happening is that Q is a function of all the little q's, p's and t's, and P is a function of all the P and T. This is my change of variables. I would like to make this change of variables in such a way that the Jacobian determinant as a matrix has determinant +1, and I would like to preserve the structure of Hamilton's equations. This is guaranteed in two different ways. One of them is to simply say that if this set of equations is true, I would like to have a new set of variables such that the following is true, such that on the one hand I have this, on the other hand I have not h but some k of Q, P and T, some new function k which is a function of the new coordinates, new generalized momenta and maybe time, such that Qi dot equal to delta k over delta Pi, Pi dot equal to minus delta k over delta Qi, and we would like to have delta of Qp over delta of Qp equal to +1. Incidentally, we would like the transformation to be invertible, because if I am going to solve the problem by going to the new variables, after finding the solution I would like to get back to my old variables and ask what are they as functions of time. I would like to solve my original problem, so this transformation must be invertible. And of course if this determinant is non-zero, then this transformation is at least locally invertible everywhere. So I would like to have an invertible transformation from little q little p to capital Q capital P, such that this property is satisfied and the structure of Hamilton's equations is also satisfied. After that I need to tell you, given capital H, the Hamiltonian in the old variables, what's k, what's k in the new variables. I need to tell you this, I need to give you a prescription. It is not obvious that capital K is just capital H in which little q is expressed in terms of capital Q's and P's and T's. Not obvious that that is true. That is only true if you did not have a T dependence here, then this is true. You could simply solve this, invert this set of problems, invert this set of transformations. So this would imply that little q is equal to a function q of capital Q's and P's, and little p is a function of capital Q's and P's, and then put that into this H and call that function k. That would be true provided you did not have T dependence. When you have T dependence, then the algorithm for finding capital K is a little more complicated than that for finding the original in the autonomous case. But for the moment we will do this in complete generality. Okay. There is some function k which can be found from capital H such that this set of equations is satisfied and this is true. A transformation which does this is called a canonical transformation. And I am going to abbreviate it by CT. Okay. We are going to use canonical transformations at length a little bit, so it is important to understand what is being implied here and what is the motivation for doing this. The motivation is I would like to be able to solve Hamilton's equations. They are a set of 2n coupled differential equations very nonlinear, but I might be able to exploit certain symmetries in the problem and reduce the problem to a lower dimensionality by solving some of the equations. In particular, if it should so turn out that in the new variables some particular q is missing, then that derivative is 0 here and this is immediately a constant of the motion. So this is the motive. Now what is the best I can do? How many such constants of the motion can I find? N of them. I mean if k does not depend on any of the q's, then all these fellows are constants of the motion, and I have straight away found n constants of the motion immediately, and it turns out that is necessary and sufficient for the problem to be integrable. So the whole point of doing canonical transformations is to check if I can make a canonical transformation such that the Hamiltonian, the new Hamiltonian, does not depend on the new generalized coordinates at all. But I would like to preserve these properties of a flow in phase space which is volume preserving, which preserves the structure of Hamilton's equations and so on, and that is done, not always possible. When it is possible, it turns out you can go the whole hog and you can make all the q's cyclic coordinates. I will give a criterion for it when this can be done, okay. But before that I would like to point out that there is another way of defining a canonical transformation, an equivalent way which does not say anything about this structure, but it says this property is true. I started writing that down, and 2, the canonical Poisson bracket relations are true. In other words, you should be guaranteed that qi qj equal to 0 equal to pi pj and qi pj equal to delta ij. So if that is true, then also this magic is attained, namely the transformation is guaranteed to be a canonical transformation. One often uses this, and the reason you often use this is because you do not want to restrict this to any specific Hamiltonian. We are talking in generalities now. We are saying you give me a system with n generalized coordinates, generalized momenta, and some given Hamiltonian, then I make a canonical transformation such that the new Hamiltonian is simplified, and I do that without reference to the Hamiltonian by simply saying these conditions are satisfied. Okay. Now there is no reference to any particular Hamiltonian here, but you are guaranteed that if this and that are true, then for every dynamical system, Hamiltonian system with n degrees of freedom with those generalized coordinates and momenta, the transformation is guaranteed to be canonical. So you can easily see that there are some transformations which would be canonical for a given Hamiltonian, but there are other transformations which would be canonical for all Hamiltonians independent of what the Hamiltonian is. Here is one. Suppose I set q equal to p and p equal to minus q with n degrees of freedom, then of course qi is equal to little pi and so on, but look at it in 1 degree of freedom. What happens now? What happens to this guy? What happens to qp? That is equal to p with a minus q, but that is equal to minus a p with a q. But we know that the Poisson bracket of A with B is minus the Poisson bracket of B with A, and therefore this is equal to q with p is equal to 1. So that is satisfied. That is satisfied. And what does the Jacobian matrix do? Delta qp over delta qp, this is equal to, we want the determinant, is equal to determinant of delta q over delta q, delta q over delta p over delta q, delta p over delta p little p. Now what is this equal to? But q does not depend on little q here, so you get a 0 there, you get a 0, and then a capital Q on a p gives you a 1, and a p on a q gives you a -1 and then a 0 again, and that is equal to +1. So this is a canonical transformation, and now you begin to see why I said it does not matter what you call the coordinates and what you call the momenta. This is a system with 2n dynamical variables. In pairs the variables are being identified and they have a certain geometric structure, and that is it. And you can see this is a masterly classic example of what is happening. So what I call the old coordinates I could call minus the new momenta, and what I call the old momenta I could call the new coordinates, and everything is unchanged. Nothing is changed whatsoever. That is a canonical transformation, an extremely simple canonical transformation. Yeah.
So what advantage is this?
No advantage. This does not get you any advantage at all because it has not reduced anything, doesn't it? But the point I made here was to show you that you have such a trivial linear canonical transformation, it does not do anything, it is not going to reduce variables, it is not going to do anything, but the fact is it does illustrate the point that in Hamiltonian dynamics the distinction between momenta and coordinates is rather artificial. What you start off as generalized coordinates and momenta can be inverted, and it is just the same problem all over again. Now I am not talking about physical dimensions, that is a different problem altogether, because I am assuming that all these are dimensionless quantities. So every quantity that I take I divide by some characteristic momentum or length in the problem, coordinate dimension in the problem, and make them all dimensionless variables. So I have assumed I have done that, but that is always doable, so there is nothing. There are other such examples of transformations, but this particular one does not do anything very big. First of all, it is a linear transformation and it is a rather trivial one, but I brought it out just to show you that the distinction between generalized coordinates and generalized momenta is an artificial one in some sense. You can actually, you have 2n variables and they are paired together in conjugate pairs, that is important structure, but which one you call the momentum and which one you call the coordinate is irrelevant completely. Is this clear? Okay. Of course in real life we are going to look at more complicated transformations, this is an utterly trivial one, so it is not going to help very much. And now let us go on, we are going to say a lot more about canonical transformations. Let me go on. And tell you when the problem is completely solvable and what is the criterion for it. The theorem itself is very hard to prove as to when you can solve this problem completely, but I will state the theorem, and this is a very famous one, it is called Louisville Arnold integrability. And it says the following. First point is, and I will illustrate this, if you can make a canonical transformation such that all the q's are cyclic variables, then this set of equations is completely solved. It's really totally solved completely, and I will illustrate that very shortly. You might ask, look, how did I do this? I am giving you n constants of the motion instead of 2n minus 1, and I am claiming the problem is totally solved, and that is very trivial to see, and I will show you how that happens. But what the criterion for integrability says is the following. It says if there exist n, and this is important, n, just n, not 2n minus 1, n, functionally independent by that I mean one of them should not be the square of another. You are going to tell me the Hamiltonian is a constant of the motion, but h squared, h cubed, e to the power h are also constants of the motion and they are not independent. So you can't say that the problem is solved just because you have functions of a given constant of the motion, they must be independent, functionally independent. COMs F1, F2, Fn. Let me just call them F1, F2. It is very convenient to choose F1 equal to the Hamiltonian. We know that already, that it is a constant of the motion in autonomous systems. So if there are n functionally independent constants such that There are other conditions one puts on it, namely they must be nice functions, they must be differentiable, they must be twice differentiable and so on. We will keep that in reserve. We will see they should actually be analytic in all these variables, we assume that for the moment, such that the Poisson bracket of Fi with Fj equal to 0 for all Ij. Every constant of the motion, every Fi, Poisson commutes with every other Fj mutually, they all their own Poisson commute. Then if this is true, then there exists a CT, a canonical transformation, such that Hamilton's equations are completely integrable. By that I mean you can explicitly solve all these equations, write down all the q's in principle as functions of t, q's and p's as functions of t. This is a necessary and sufficient condition. You need these guys to be functionally independent and you need them to have 0 Poisson brackets with each other. Now two quantities A and B, or F1 and F2, their Poisson bracket is 0. I have been saying they Poisson commute, but I also pointed out that there is another term, they are said to be in involution with each other. So what is needed is n constants of the motion in involution with each other, and the first thing you have to understand is that this operation of commute two quantities with 0 Poisson bracket is not one of those operations which would have this property of associativity, namely, or reflexive, whatever you call it. That is, if A Poisson bracket B is 0 and B Poisson bracket C is 0, it is not guaranteed that A Poisson bracket C is 0. This is not guaranteed. It is very easy to see that this is not true, but you can use the Jacobi identity, and then of course when you have two constants of the motion you can discover a third, because it is clear that if I took A with BC plus B Poisson bracket CA plus C AB, this is equal to 0. This was the Jacobi identity, right. Now suppose A is a constant of the motion and B is a constant of the motion and C is chosen to be the Hamiltonian, that is also a constant of the motion. So C is the Hamiltonian, B with H, but if B is a constant of the motion and they are all time independent, then this is 0. Similarly C was the Hamiltonian, so you have H with A, and this was also 0, and C is the Hamiltonian. So what does that imply? It says that H Poisson bracket with the Poisson bracket of A with B is 0. What does that imply? The Poisson bracket is itself a constant of the motion. So it says if you have two constants of the motion other than the Hamiltonian, then their mutual Poisson bracket is another constant of the motion, and then you can use that to create more Poisson brackets and so on, and therefore an algebraic structure is evolving. So it is possible that in some problems you may be able to exploit this to go on and find other constants of the motion. In fact, if you look at the angular momentum, L sub x in many problems is a constant of the motion, L sub y is a constant of the motion, and this will imply that their Poisson bracket, which is L sub z, is also a constant of the motion. That is why if two components of the angular momentum are constants, the third is also a constant of the motion, and it follows from this. Of course it might fizzle out, it might turn out that this guy here is either 0 or a number. If it is equal to 6, then we know 6 is already a constant, it does not matter. So it could turn out to be trivial in some cases, but it is also useful in many other cases because it helps you generate more constants of the motion. But what is asked here is n of them functionally independent, and after that the claim is the problem is solvable. This is the purport of the theorem, Louisville-Arnold theorem. Now solvable in what sense, and what does this canonical transformation do? What it does, I am not going to prove this theorem by the way, but I am going to show you how the problem becomes solvable if that is true. Let us assume that this theorem is true, this is given, then it says there exists a canonical transformation such that the problem is solvable. It does not tell you most notably how to find these constants of the motion, and it does not tell you even worse how to find the canonical transformation at all. So this is more like an existence theorem. It really is guaranteeing you that there exists something, but it is hidden and you do not know where it is, but it exists, you know the problem is solvable. Now what does it imply and how does it get solved? Well, in such cases it turns out that the canonical transformation has a special name, and it is called action angle variables. So really instead of Q and P, you go to capital Q and capital P, and the standard notation for this is not capital Q capital P, but rather theta and I. And remember there are n of them, little I, the subscript I has to be put in, and these thetas are called angle variables and the capital I's are called action variables. I will explain why this is true, and we will also look at a simple example. So these are called angle variables, this is called action variables. And this transformation, this canonical transformation which does this magic, is called a transformation to action angle variables. But the way the magic operates is as follows. It turns out that once you do this canonical transformation, then k of theta I becomes equal to k of I alone. No dependence on half the variables, on the new generalized coordinates, no dependence at all. What does that imply? Because we can write the equations of motion down, it implies I know that theta I dot equal to delta k, which is a function only of I1 up to In over delta II. Instead of capital Q and capital P, I am going to use theta and I here, and II dot equal to minus delta k of I1 In over delta theta I for little I running from 1 to n. If this is possible, if this happens, then what is the consequence of this equation? This is immediately 0 because this has no dependence on the thetas. So this is equal to 0. What does that imply? This implies I1 equal to constant of the motion, In equal to constant of the motion, little n. All the I's are constants of the motion. The new generalized momenta, which I have called action variables, they are constants of the motion. If that happens, then what is this guy equal to? What does that imply? What is this equal to? What does that give you? Well, what can this be a function of? After you differentiate, what is it a function of? Of the I's, some function of the I's, right? So all these guys are function of the I's. What shall we call them? What shall we call these functions? Some function of I1 up to In. Each of them, each partial derivative is some function. I already call these angle variables for reasons which I will explain later, and this is the rate of change of an angle. So what should I call it? Some omega, let us call it some omega. Looks like an angular velocity, so let me call it omega sub I. Do the omega i's depend on time? No, because the i's are all constants of the motion. For a given set of initial conditions they remain unchanged in time. So what is the solution to this equation? Of all the i's, t plus theta I of 0, and the problem is solved. What are the new constants of the motion? You need 2n constants. You need, in 2n dimensional phase space, you need 2n constants. We found n of them and they are I1 to In. Actually we started by saying there exists f1 to fn already, and these i's need not be the same as the f's, but you are absolutely guaranteed that the i's are functions of the f's, combinations, some functional combinations. There are n of those and there are n of these. So we already have n constants of the motion which are time independent. Where are the other constants of the motion? The theta i's of 0 are all constants of the motion. So all these quantities, theta I minus omega I t, these are all constants of the motion. These are functions of i's, by the way. They are time dependent, just like our one dimensional example had time dependent constant of the motion. In this case, in a fully integrable Hamiltonian system, this is called a fully integrable Hamiltonian system, you have n constants of the motion which are time independent, the action variables, and n more which are time dependent explicitly, but the time dependence is linear, extremely simple. And we will see what is going to happen. Why I am going to call this an angle variable will become very clear, because we are going to look at bounded motion, we are going to look at motion in a bounded phase space, essentially oscillations of some kind, generalized oscillations, not free unbounded motion. Then these thetas will indeed turn out to be angles, and the problem is fully solved, you can see. Now the only thing that changes are n angles, and if I tell you now by anticipating myself that these angles go from 0 to 2 pi, then what sort of phase space do I have? I have a phase space which is determined by n angles. From the 2n dimensional phase space I change variables to a new set of variables, and this set of variables is just n angles, each of which goes from 0 to 2 pi independently. If you had one angle, what would the phase space look like? A circle, on a circle. If you had two angles, what would it look like? No, because if you have two angles on the surface of a sphere in 3 dimensions, you have an azimuthal angle, the longitude, which goes 0 to 2 pi, but the polar angle goes only 0 to pi. But I have two angles going 0 to 2 pi, a torus. So you have one angle like that and another angle like this, and at each point on this circle you have attached a circle at right angles to it, and that is a torus. That is topologically equivalent to a donut, the surface of a donut. And if you have n angles, you have an n torus. So this is why we say that Hamiltonian dynamics for a fully integrable system takes place in a phase space on some n torus, n dimensional torus, and that is starting to play a very fundamental role here. We will see in a little more how this really comes about, but the problem is actually solved. Now this happy situation, I am sorry to say, applies only for two cases, the harmonic oscillator and the Kepler problem in 3 dimensions. In general this is not true, but it is very important to see where this will break down, because that is what the whole thing is about. Most systems you would start with something solved. It is like quantum mechanics, you start with a hydrogen atom, but how many situations do you have in which you have one hydrogen atom and nothing else in the universe, but you need the hydrogen atom in order to do everything else by perturbation, and that is exactly what is going to happen. I now leave you finally with the following exercise, then we take it up from here tomorrow. If you took the simple harmonic oscillator, so example linear harmonic oscillator, and the Hamiltonian in QP is equal to p squared over 2m plus 1/2 m omega squared q squared. Of course you can solve this problem without action angle variables. This is a trivial problem, right? Even for the JEE you need this problem, a solution to this problem, but now let us use a sledgehammer to crack a nut and solve this by going to action angle variables. Now I have to tell you what the answer is in order to tell you what the action is. There is a prescription for it which we will look at later on, but the change of variables is the following. It says q equal to square root of 2I over m omega sine theta. I do not swear to these things because I usually use units in which I put m equal to 1 omega equal to 1, but I think it is dimensionally right. P equal to square root of 2I m omega cos theta. This is not going to polar coordinates, by the way. Incidentally, if you are on a plane, a system with 2 degrees of freedom x and y and 2 momenta px and py, going to polar coordinates on this plane is not a canonical transformation. Why is that? Why is that? Right away you can say, choosing just in real space, going from xy to r theta is not a canonical transformation, and correspondingly going from px py to pr radial momentum and angular momentum, that's not a canonical transformation. Area is not preserved, the Jacobian is not 1, magnitude is not 1, so that's right away rules it out. This looks like going to polar coordinates, but it's not, it's in phase space, and it's got the square roots and things like that, and it's not hard to show that h of qp goes to k of I, which is equal to I omega. Check that out, it is very trivial because you just have to write q squared and p squared and plug that in here and immediately you get omega. So this new Hamiltonian does indeed have theta as a cyclic variable, it is only dependent on I. Of course you can invert this whole business, so I is equal to this divided by omega, and you can also see that tan theta, if I divide one by the other, then there is a 1 over m omega, so this is equal to m omega q over p, or theta tan inverse and I equal to p squared over 2 m omega plus 1/2 m omega q squared. So these are the new variables theta and I. I leave you to verify explicitly that the Poisson bracket of theta with I equal to plus 1, it should be. So these are the action angle variables, and the problem is trivial because now all I have to use is Hamilton's equations here, and it immediately tells you that I is a constant and theta is, yeah.
If I choose to solve these equations numerically,
Yeah.
I still need the level.
No, it depends, it does not help very much. When you solve numerically, it might help to go to a canonical transformation in which part of the q's are cyclic coordinates.
But that is only making my computation simpler.
It is not making it simpler because it is very hard to do numerical integration in which you preserve the volume. So this structure of Hamilton's equations has to be preserved, and that is not trivial numerically. So the numerical routines for solving Hamilton's equations would have to be such that the integrators are symplectic integrators, that you really preserve the structure of Hamilton's equations, that the volume element is preserved, the canonical structure is preserved, and this is a non-trivial task, very non-trivial task. It is important to do this because if you look at accelerators and you have these particles zooming around, then you would like to solve the equations of motion numerically. The system is very complicated, you would like to solve it numerically, but then in a minute or so you would have large errors multiplying system your calculation unless you are very careful to preserve the Hamiltonian structure. So it is a very non-trivial problem in accelerator physics to get numerical packages of integration where you preserve the structure of Hamilton's equations, highly non-trivial problem. A lot of work has gone on that, but my point here was to tell you, to start telling you where this whole thing is going to break down, where chaos is going to come from in this, and for that this is needed, this portion is needed. You must appreciate the torus structure of phase space for integrable systems, and then slowly we will get rid of this as we go along. The next step is to ask what happens if I put 2 oscillators, and this would be on a 2-dimensional torus in 4-dimensional phase space, and it is a little hard to visualize, but we can still do it, and some surprises are in store. but this is the action angle variable transformation for a linear harmonic oscillator. I urge you to show explicitly, solve this, go through the routine, solve it, but above all show that the Jacobian of this transformation is +1 and that the canonical Poisson brackets are preserved. So that is a useful exercise in handling Poisson brackets. Okay. So let me stop here and we take it from this point tomorrow.